guys, it's me. This video is for the practice exam, problem 2. And I'm just gonna go through it slowly and carefully. And if anything is confusing, please email me, okay? I want every single one of you to understand how to do this. And I know you guys are capable because really you're rock stars. You're my inspiration in so many ways. I feel so honored to be your teacher, okay? You can totally handle this. Okay, ready? So here's the question. My brother holds a water balloon on the roof of a 30-meter high building, which he would do, by the way, if you know my brother. I'm kidding, I love you, Moshe. He then throws the balloon 30 degrees above the horizontal with an initial velocity of 10 meters per second. Okay, so the first thing we do is we draw a picture. All right, y'all know how to draw a picture. That's a huge part of our class is drawing pictures. So he's on the top of a 30-meter high ledge, or not ledge, building. Can you see that? Yes, you can. Awesome. And here's my brother, and here's his yarmulke. Go. And here's his water balloon. Okay, he's holding a very big water balloon. All right. No comments in my drawing. All right, awesome. So he's going to throw it 30 degrees above the horizontal. Now remember, the horizontal just means the x-axis. I'm going to write that down so you know this. Horizontal, okay, that's the same thing as saying the x-axis, okay? Just like vertical is the same thing as saying the y-axis. This is true forever and ever, amen, okay? And I know it's a little bit confusing for some of you because oftentimes I write down x to mean position or y to mean position. And then I'm like, oh, I want the x component of velocity or the y component of velocity. And you guys are like, wait, I'm confused. I thought x was position. Velocity is totally separate. And the answer is that you're right, except that I use x and y to mean position because it's position physically in the sense that when I draw my x position on a graph, that's how far I've gone. But the thing is, when I want to represent a component of any vector, like velocity or acceleration, I use it on a graph as well. And so in that case, I'll write v sub x or v sub y, okay? Which is why, in this case, right, when I draw my velocity, I'm going to ask for the x and y components of it, but that's to come, okay? So he's throwing the balloon 30 degrees above the horizontal. So here's my horizontal, okay? Here's my x-axis, and here's my vertical. This is my y-axis, right? And he's going to go 30 degrees. So he's going to start here, and he's going to go 30 degrees, okay? So 30 degrees, like so, 30 degrees. Okay, awesome. So, above, and the initial velocity is 10 meters per second. Now, what I'm doing, I'm giving you a vector, okay? So the vector is velocity. So my initial velocity vector, okay, vector, is described right now, okay, as 10 meters per second. That's my magnitude, okay, and 30 degrees, okay, above x-axis, okay, this is my direction. But you see, all we're doing is describing my initial velocity vector. So the magnitude of this is 10 meters per second. It's a little hard to read, but you should have your own picture drawn as well. So you should, use that. I hope this helps. Okay, awesome. So I want to know the x component of velocity as the balloon falls. Now, notice, you could be like, hang on a second, Miss Mizrachi, how do I know the x component of velocity as the balloon falls? Do you mean the beginning velocity? Do you mean the end velocity? Do you mean the max velocity? And the answer is this. Remember how your x and y components are completely independent? So that means that the acceleration in this whole problem, right, is only gravity because I'm letting go of it and then it's going to accelerate. So my gravity doesn't act in the x component, does it? It only acts in the vertical. So literally, my x component of velocity does not change throughout the entire trajectory. Everywhere you go, from the top to the bottom to the middle to the end, the direction horizontally in the x direction, right, is constant, okay? So let's find what that is. Now we're going to draw our initial velocity vector, okay? So this is my initial velocity, okay? And that's 10 meters per second, okay? And it's 30 degrees above the horizontal, above the x-axis, okay? So we're going to draw our little triangle here and use Pythagorean, or actually, you know what? We'll use cosine, okay? So now cosine of 30 degrees, okay, is equal to, this will be my x velocity, and this will be my y initial velocity, okay? That v naught y just means the initial velocity in the y direction, because of course my y velocity is changing. And we know our x velocity is constant, so all I have to do is say v sub x. So cosine of 30 degrees is going to be v sub x, right, which is going to be adjacent over hypotenuse, which is 10 meters per second, okay? So now I'm going to solve for this v sub x. Cosine of 30 degrees is radical 3 over 2. So that means, so we'll say this equals the square root of 3 over 2. So that means that v sub x, right, equals 10 times the square root of 3 over 2, right, which is just 5 times radical 3, okay? So the x component of velocity is always going to be 5 times the square root of 3 in this situation. It's not going to change because there's no acceleration in the x direction, okay? Awesome. I want you to take a look at that, make sure it makes sense to you, make sure there's no questions here, and then we're going to move on. Okay? Moving on. So now we want our y component of the initial velocity. What's the y component of the initial velocity? Notice how I underlined the word initial? That's because I want you to know that the y component of my velocity is what's going to change, right? Because gravity acts in the y direction, not the x direction. So that's the only thing that's going to vary. Or that's not the only thing that's going to vary, but only the y direction is where we're going to have any variation at all, okay? So when I want the initial velocity, again, in the y direction, I'm looking for this v naught y. Again, 10 meters per second. I just do the same thing that Shani did in our class so beautifully today. I say v sub y equals 10 meters per second, and in this case I'm going to use sine theta, right, because sine of 30 is opposite over adjacent, and if you do the algebra on your own you'll see that this works, right? So it's 10 meters per second times sine of 30 degrees, which I believe is 1/2, so that's 10 meters per second times 1/2, which is just 5 meters per second, okay? And this is also meters per second, I apologize, check. And that is equals our initial y component, okay, of velocity, okay? So this, if I were to imagine this was two balls, right, not just one, that happen to overlap each other and affect each other because they're on the same time stream, right? And I were to say my ball that's affecting the y direction is just going up and down, okay? That's all that it's doing. It's going like this, and the other one's going like this, right? So this one here has an initial velocity of 5 meters per second, okay? Beautiful. So now we have A and B. Okay, we're already almost done. So now we're going to do problem C. Okay, what is the maximum height the balloon will reach? Now this is one of those problems where you have to consider the physics, okay? What is the maximum height that the balloon will reach? Do you guys remember how in our demo we threw a ball up in the air, and when we threw it straight up, there was that instant where it hung, right, in midair, and it wasn't moving at all. And that's only when it's going straight up. Now in this case, that means that it loses all of its y velocity at the very top of the trajectory. So it's going to be a parabola. It's going to look something like this, and then it's going to fall down, right? But when it gets to this point, the y velocity is 0, even though the x velocity, of course, stays constant. So if we want to know the maximum height, we're just looking for the time, right? Or what is the maximum height? We want the y position, okay, when the y velocity equals 0. That's what we're looking for. So we want to know what the position at which all of this initial 5 meters per second in the up and down direction is gone. And so if we want that, we realize that we have constant acceleration in the y direction, right? And that's gravity. And again, this is totally separate from the x direction, okay? So we're able to use our constant acceleration equations only when dealing with the y component of velocity, okay? Or y component in general. So because we have constant acceleration in the y direction, all right? So that means that our y acceleration equals constant, okay? And as you guys know so beautifully, that's g, which is 9.81 meters per second squared, okay? So this is what we're going to use, okay? So I'm looking at my equations. Let me see if I can find a cover page and I'll show you guys. Let's see. Here we go, perfect. See this? All right, so I'm looking at these. Now, what do I have that will help me? So I have my constant acceleration, right, equations right there. Now, what do I have? I have my final velocity, right, because I know that I want it to be 0, right? I have my acceleration, right, because it's in the y direction, because it's just the acceleration due to gravity. And what I'm looking for is my change in position, right, when my final, I have my initial velocity and I have my final velocity, right, which is going to be 0 because I want to know the height, right, when this is going to be, when my velocity is 0. I'm sorry. So I have my change in velocity, I have my acceleration, and I'm looking for my change in position. So the equation that I want to use is this one, right? It's the only one that doesn't, we don't care about time at all. So this is the one that we're going to use, okay? So that means that we have the final velocity squared equals the initial velocity squared plus 2a times the change in x, right? Or in this case, we'll make it y because it just makes it easier. Now, we want the y position where the y velocity is 0, right? So that means that our final is going to be 0. Our initial is going to be the y component of velocity, which is 5 meters per second. And again, this is going to be squared. Plus 2 times our acceleration in the y direction, which is 9.81 meters per second squared, times the final y position minus the initial position. We'll take the initial position to, you know what, I'm going to take what Joe did in class today, and we're going to use our initial position as 30, okay? So our y final minus 30 meters, because that's the initial position, height in the air. That way we actually get the right answer, okay? So let's solve this, okay? Then we get 0 equals 25 meters squared per second squared, okay? Plus 2 times, we'll make this about 10, just to make it easier for me. So plus 20 meters per second squared times y final minus 30 meters. Remember that it's that this y final is what we're looking for. So now we're going to subtract 25 on both sides. We get minus 25 meters squared per second squared equals 20 meters per second squared times y final minus 30 meters. Okay, we'll multiply this through. So we'll say this equals 20 meters per second squared y final minus 20 times 30 is, I think, 600 meters squared per second squared. Then we're going to add this, and this is negative 25 meters squared per second squared. We're going to add this up, and you guys can really solve this yourself, but you're going to get, one second. I'm just thinking if you should be adding this or subtracting this. You know what I would do? The problem with doing it this way is that the directions get mixed up. So even though Joe was right in the sense that you really can add, just put your y initial here. And if you did it this way, by the way, and solved it this way, I would give you full points because you technically would be correct. But the only problem is your negative signs mix you up just because it goes up, right, and then down. And so it takes our downward direction of position, right, in the positive and our upward in the negative because we chose that by convention. But we want the position from the ground overall. So I'm going to say that this is not the best way to do it. I'm going to say that instead we should take our y initial to be 0 and we'll just add it to the 30 in the end. Okay, so we'll take this and we'll just make this like this will be 0. Okay. And then we get, our y final, right, is then going to be 25 meters squared per second squared divided by 20 meters per second squared, which is 5/4, excuse me. And then again, the second squared goes away, and we just get left with meters. Okay, 5/4 meters, and that's above, right, our initial 30 meters. So our total height, so our position, so our highest point, max height, okay, is just going to be 30 meters plus 5/4. All right, meters. Awesome. That wasn't so bad, right? Not too painful. Now the next problem. At the maximum height, what's the balloon's velocity? This is a bit of a trick question, right? Because remember, at the maximum height, our y velocity is all gone, right? Because it's used itself up. Gravity has taken it to the very tippy top, which is why it turns around and comes back down again. So all that we've got left is our x velocity, right? So that means that our v at the highest point, by the way, this is always true anytime we have free fall, is going to equal, okay, v sub x, which we found because all the y velocity is gone. All we've got left is the x velocity. So that's got to be all that we've got left over. That's got to be the velocity at the maximum height. So our v at max height, okay, is just going to be 5 meters per second in the x direction, right? So we're going to say x direction, You could also write down 0 degrees from the x-axis. You could also write down just x with a hat on top of it, whatever you want, as long as you indicate to me that you know your magnitude and your direction, okay? Because again, it's a vector, and that's it. All right, this isn't so bad so far. Now let's do E. How long does the balloon take to reach its maximum height? Well, we already found, right, the maximum height. We already found the initial and final velocity to get to that height. We found the acceleration. We literally can use any one of these equations and we'll get the right answer because we have everything except for the time. I'm going to choose to use this equation just because it's kind of I think it's the simplest, but you can use whatever you want, okay? So our acceleration, again, maximum height, we're only going to deal with the y direction, right? Because the y component is y, it's what's limiting the height that it can go, obviously, because the height is in the y direction. Does this make sense? I think this makes sense. You guys are probably getting bored and like, Ms. Mizrachi, why are you repeating yourself? Come on, we're ready, we got this, move on. And I'm sorry if I'm boring you, but you know what? I work for NASA, I can do what I want. All right, awesome. So, and this is great, this is kosher. Okay, so acceleration, we know this, is v final minus v initial divided by the time, okay? Again, we only care about the y direction in this case, so we want to know how long does it take to reach its maximum height. So of course our acceleration in the y direction is 9.81 meters per second squared. We're going to say this is about 10 meters per second squared just because it's easier for me. You can't do this on your Regents, but you can do it on my exams. And this is going to equal the final velocity minus the initial velocity. And again, we only care about the y direction. So this is the y component of my final velocity, and that's going to be 0 at the maximum height, right? Minus the initial y velocity, not x, just y, because we only care about the y by itself. We don't care about the x, but this is like 2 separate balls. So the one that's going up and down is just 5 meters per second. We solved that before, right? And that's divided by the time, which is what we're trying to solve. If you mess this around with algebra, you just get time, right, equals negative 5 meters per second because of convention of direction over 10 meters per second squared. Since time can't be negative, you can drop the negative sign, don't worry about it. And so you just get, right, you get 1/2 seconds. Isn't that beautiful? Half a second, not too bad. All right, we're almost done, guys. We're chug-a-lugging. Now we're gonna do number F, or letter F, whatever. You're lucky I didn't use Greek. How long does it take for the balloon to hit the ground, okay, right? Now, if we look at this picture again, right, we have, so here's the tower, right? And here's where it's going. Bop, 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 bop. We already know the amount of time that it takes to get here, right? We just found that. That's t equals 1/2 second, okay? Now we want to know the time that it takes for it to go from here. Now, at this point, remember that its y velocity equals 0. And remember that a ball thrown horizontally with a constant velocity, straight out, takes just as much time to hit the ground as though it was dropped from rest because there's no y component of velocity. So I can just treat this as a problem where I want to know the amount of time it takes to go from here, right, to here, just straight down. And the way that I do that, right, is I can use my equations. Let's see. Let's use, well, what do we have, right? We have our initial velocity is 0 in the y direction. We're looking for the amount of time, and we have the height, right? Because it's just going to be, we know that our y, right, here, this position here, is going to equal, what did we say, 30 meters plus 5/4 meters? Which is just, we should probably solve that. That's 30 times 4 is 120, plus 5 is 125, so that's 125 over 4 meters, okay? Right. So, and that's going to be our height. So all that we want to know is the amount of time it takes for a ball dropped from rest to fall 125 over 4 meters. And to do that, we're going to use the equation that has our position, right? Has our initial velocity and an acceleration and time. So this looks like a perfect shidduch. So we're going to use this one, okay? So we want y final, right, is going to equal y initial plus v naught sub y times time plus 1/2 at squared, okay? Now this equals 0, right, because we're dropping it in the y direction. There's 0 velocity at the peak, and we're going to find the time it gets to go from here to here. Our y final is going to, and y initial, right, if we subtract these, we know the change is going to be 125. So we can treat this as 0, we can treat this as 125. It's up to you, I don't really care. I'm just going to say this part is 125. We're going to choose this to be the positive direction, right, is going to equal this part, right, and this is going to be 0. And so all we get is that, and then this part's down here. So we're going to say 125 over 4, right, equals 1/2 at squared which is 1/2, we'll round gravity's acceleration to 10 meters per second squared times the time squared, which is what we're looking for, okay? Which means that our time squared is just going to be 2, right? Because we're going to multiply both sides by 2, times 125 over 4 times 10. And that's just algebra. If you do it yourself, you'll see that it works, because I multiplied 2 by both sides, and then I divided 10 by both sides, okay? So this is meters per second squared, and this is meters. Meters. Okay? And that's just going to equal, the 2 goes away. We're going to get the 2 down here. What can we pull out of this? We can pull out a 5, and we can get 2, and 125 divided by 5. 125 is 15 squared. So it's going to be 15 times 3, which is 45, I think. Let me just check that. Hang on. Y'all are being very patient. Thank you. It's going to be, let's see. Oh, excuse me, it's 25. I'm sorry. Yes, it's 25. So we're going to get, which is going to be 25 over 4. Which means that the time that passes is going to be 5 halves. All right, which is roughly 3. It's 2.5, which is exactly what Moore said during class. So he was right on track where you should be. Okay, good. So the time that it takes for it to go from here to here is 5 seconds, and the time for it to go from here to here is 1/2 second. So that means that the total time that it takes, which is what we're looking for it to hit the ground, is going to be 5 halves plus 1/2, which is 6 halves, which is 3 seconds, which is exactly what Moore said during class, so he was right, and you guys should know that. So that's correct. So if you go up to the top, fall down again, it's going to take you exactly 3 seconds before you hit the ground, okay? Awesome. Very good. All right, moving on. Let's do G. How far from the foot of the building does the balloon land? Well, now, okay, that question is easy because it spent 3 seconds in the air. So we just want to know the distance that it can travel, right, with the constant x velocity in that amount of time. In other words, once it hits that maximum distance, it's not allowed to go anymore, right? That's the furthest you can go with that constant x velocity, because once you've splat, you're done, right? So when we want to know how far from the foot of the building does it land, we just say, how far can you get while going the constant velocity that's in the x velocity in the amount of time allowed. So the amount of time that it's going to spend in the air, right, we already said, is going to be 2 seconds, right? That's the total time that we allow it to have, okay? So, is that right? No, I'm sorry, it's 3 seconds. I apologize. 3 seconds, okay? 3 seconds. And its velocity, let's see what its x velocity is. It's 5 radical 3. So its x velocity v sub x, right, equals constant, and is 5 times the square root of 3 meters per second, okay? So I want to know the distance that it can go with this constant velocity, and for that I just use v equals the change in position over time, right? Which means that the change in position is just equal to the velocity times the time that it takes to get there, which is just equal to 5 times the square root of 3 meters per second times 3 seconds, right? Which is just going to be 15 times the square root of 3 meters, excuse me. And that's going to be the distance from the foot of the building, right? And what is the final velocity of the balloon as it hits the ground? Well, for this, you're going to have to use another one of those equations, because for h, right, you already know the x velocity that it's going to have as it hits the ground, right? The velocity sub x equals constant, right? And that's equal to 5 radical 3 meters per second. Meters per second, okay? And that's constant x velocity. So the y velocity, right, at this point is what we really care about. Now, we have, let's see, what do we want to use now? You know what, let's use this equation. We can really choose, because we have everything. We have the time, we have the position, we have the we're trying to find the final velocity, and we have the initial velocity. So let's just choose to use, this equation. Okay, so it's a v final squared equals v initial squared plus 2a times x final minus x initial. And again, there's a lot of ways to do this, so if you don't do it my way, if you don't like my way, you're like, Miss Mizrachi, I don't like your way, I want to do it my way, I'll be like, all right, do it your way, that's fine, okay? But the way I'm going to choose to do it is I'm going to say the velocity that it would have in the y direction if I was to drop it from 0 initial velocity, which is at this very tippity top of the trajectory. So if I were to drop it from here at where it starts with 0 meters per second, like what's going to be its velocity at the very end, okay? That's what I'm going to choose to do. So that means that my velocity initial is going to be 0, okay? My velocity final is what I'm looking for in the y direction, okay? And I have plus 2 times, we're going to say again 10 meters per second squared, even though it's approximation, times the height that it's going, which is just 30 meters plus 5/4 meters, because we said that's how much this equals. So it's 30 plus 5/4 is whatever 30, it's going to be, I'll just do the math really quick, plus 5 over 4. 4 times 3 is 12, 120, so it's 125 over 4. So it's 2 times 10 meters per second squared times 125 over 4, okay, which is just equal to 20 divided by 4 times 125, which is just going to be 5 times 125, which is going to be, I really should have a calculator, but this equals the v final squared in the y direction, okay? So that means that, well, the square root of 125 is, I think it's 15. It's 15. I'm almost positive it's 15. So this is going to be equal to 5 times 125, right? Which is just going to, which means that the final velocity in the y direction, right, is the square root of this, which is just going to be 15 times the square root of 5. All right? So that means that our final velocity, as it's hitting the ground, is just going to be, right, we're going to have this triangle here. We're going to have a y component that's 15 radical 5 meters per second, and an x component which never changed, which is 5 radical 3 meters per second, okay? And what we want, again, is this one, because it's coming down, okay? So if we want to, we can find this angle using SOHCAHTOA, so the inverse tangent of this over this, which you guys can do on your own. And what this equals, what the length equals, the magnitude. I expect you guys to find this angle. I'm just not going to do it right now because I don't have a calculator. But the magnitude of this thing, which is the v final, we're going to say v final, right, is equal to, and the magnitude of that is equal to the square root of 15 radical 5 squared, which is just 5 times 125, we said, right? Plus this squared, which is 25 times, let's see, times 3. Wow, not right. And then whatever, you guys can do it on your own, but this is what our v final is equal to, okay? So, as you can see, it's a lot. It's a very, 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 very hard problem. I'm not saying that it's easy. I'm saying it's very difficult. The problem on the exam will be not nearly as hard as this, but the reason why I gave this to you as your sample final exam is because if you can solve this problem and if you can do this problem on your own, you will have no problem at all with the exam, okay? And I believe in all of you. I know you're going to do amazing, all right? Hatzlacha Rabbah, and I'll see you on Monday.